In this lecture, we're going to go over 1.8 of our textbook, Subsets of the Real Numbers. So let's talk about what a set is. A set is just a collection of objects. So it might be we have socks, shirts, jeans. They're all in the set of clothing. And how we'd write it is clothing equals curly bracket, socks, comma, shirt, comma, jeans. We'd list the objects that are in our set. Another example would be football, golf, tennis, and basketball are in the set of sports. So sports equals the set with football, golf, tennis, and basketball. So an element is a component or a constituent of the whole or one of the parts into which the whole may be resolved. So that's a lot of language, but remember when I was talking about a set is made up of objects? Well, each of those objects that are in the set, those are an element. So football is an element of the sports set. Golf is an element of the sports set, and so on. So the elements in the set of clothing are socks, shirt, and jeans, and the elements in the sports are football, golf, tennis, and basketball. Now a subset is a set in which all of the elements are contained in another set. For example, if I say a subset of the set sports is round ball sports, that would include golf, tennis, and basketball. Golf, tennis, and basketball are elements of the original sports set, but a subset of that sports would be round ball sports. Likewise, with team sports, football and basketball would be team sports, and golf and tennis would not belong to that subset of the sports. Alright, so that's fun, but how does it apply to mathematics? We have a set of real numbers, and then we have subsets of the real numbers. So the first one we already chatted about was counting numbers. 1, 2, 3, it's the set containing 1, 2, 3, and so on. You keep counting, 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 you're not going to stop. Then we have our whole numbers, which is actually, the counting numbers is a subset of the whole numbers, because the whole numbers is the counting numbers and 0. So 0, 1, 2, 3, and so on. So counting numbers is a subset of real numbers, but counting numbers is also a subset of the whole numbers. Integers. Integers go all the way to infinity, way out to the negative, as well as to the positive, and it's -3, -2, -1, 0, 1, 2, 3. Those are the integers, positive and negative whole numbers. Then we have the rational numbers. So if a and b are integers, and b is not 0, then a over b is a rational number. Okay. Keep that in mind. Then our last subset, major subset, is the irrational numbers. Irrational numbers are non-rational numbers. But here's the definition of a non-rational number. It is a non-repeating, non-terminating decimal number. So let's see a couple of irrational numbers. -3, -2/3, 0, 0.333, and 0.75. Now, remember the definition of our rational number was anything that looks like a over b where b is not 0, and a and b are integers. Well, I don't know. -3 doesn't have anything in the denominator. 0 doesn't have anything in the denominator. There's a decimal, and there's another decimal. How are these actual rational numbers? Well, let's see why. We don't seem to have a problem with the 2/3 because that is in that a over b, and it could be negative numbers, so that's okay. So why is that? -3 we can write as -3 over 1. Hey, fits definition, we're good. 0 we can write in any fraction where a, as long as a is not 0, It can be any integer number and it still fits our definition. What about 0.333? We can write it as 1 over 3, 1/3. So that fits our definition of a rational number. And 0.75, thinking along the lines of the 1/3, well, 3/4, if you divide 3 into 4, you get 0.75, and that meets our definition. So what are examples of irrational numbers? Well, the most famous one of all is pi. That's the good old number that you multiply to get the circumference of a circle, the area of a circle. We use it all the time. So there's pi. There's e, which is used a lot in finance. That's another irrational number. We give it the name of e because it's a lot easier to use e than it is this big long decimal. And again, the decimal never repeats and it never ends. It never terminates. Square root of 2, square root of 3. And then there's this very special number, 1 plus the square root of 5 over 2. Have you ever seen this fraction? If you have, it actually has a special name. It's called the golden ratio. This golden ratio is supposed to work in music and art and architecture, and it's this golden ratio that for whatever reason our eye sees and we see something as beautiful. There's all these kinds of proofs and things out there that why we think art is appealing has to do with this very special golden ratio, surprisingly enough. So why aren't they rational numbers? Well, pi is approximately 3.1415. Okay, it does not terminate and it does not repeat. We just kind of cut it off at 3.14. E, similarly, 2.7182. Again, does not terminate, does not repeat. A square root of 2, I went ahead and carried the decimal out a little bit further. So 1.41421356237. But it doesn't terminate and it doesn't repeat. So even though I stopped writing down numbers, it doesn't stop. And here's the golden ratio. 1.6180339887498948482, and again, doesn't stop and doesn't repeat. So it is an irrational number. So here's a fun fact. October 17, 2011. How many digits of pi were calculated? Now, I know we only typically use 3.14 or even 3.1415, but how many digits of pi have actually been calculated? What do you think? A million? A billion? 10? No, it's not 10. It is so far 10 trillion digits, and they are still calculating digits. But on October 17th, 2011, computers have calculated the digits of pi out to 3.1415 with 10 trillion digits after that. It's quite amazing, actually. So what is the set of real numbers? We chatted about counting numbers, whole numbers, integers, rational numbers, irrational numbers, but we never really said what the set of real numbers is. Here it is, easy as all the rational and irrational numbers. That makes up the real numbers. So that's the end of part 1. To continue this lecture, go to part 2.